Hello, good morning to all of you in California and United States, and good afternoon to all of you in Europe. My name is Eicke Weber, and I will start our session on storage, which is of course a very important part of the total renewable energy solution. It's an integral part, and I would like to introduce into our session and our topic with a couple of slides. Okay, I would like to start with the observation that photovoltaics, which is a key pillar of our future renewable energy system, has been growing since 1992 at a really breakneck pace, 38% of compounded growth rate since 1992, and it brought us now in 2019 to 627 gigawatts of PV installed, which you could consider to be an enormous amount with the 38% slope. But of course, more will be coming. And as a matter of fact, if we observe just the last couple of years, we see that now solar PV is the renewable energy technology which experiences the most rapid growth in all of this. And this is the only slide I want to talk about this topic. Solar PV technology now comes almost exclusively out of China and Asia. So one of the points of the European Solar Manufacturing Council that I have the pleasure to chair together with Gaëtan Masson is really to look into ways to promote solar industry growth up here in Europe. And of course, the same problem we have in the United States. We are very clear. And of course, what is extremely positive is costs for solar PV electricity have come down much, much faster than anybody expected. I share with you this slide, which was from a study at Fraunhofer in the year 2015. And then we said very optimistically by 2050, we could reach 2 cents per kilowatt hour for solar generated electricity. As a matter of fact, already in 2020, we are below 1.5 cents per kilowatt hour, and we are now approaching rapidly towards 1 cent per kilowatt hour in sun-rich areas. So solar energy harvested by photovoltaics is now becoming the lowest cost way to generate electricity, period. However, solar and wind have a big disadvantage that they are fluctuating. The sun doesn't shine in the night, and the wind is as well not blowing continuously. Therefore, we have to worry about how the total energy system can look like, which is stable, resilient, and supplies power whenever we need it. And in my institute, when I was the director in Freiburg, Hans-Martin Henning, who was at that time my deputy director, he developed a model called REMOD-D to model in detail what are the needs for a country like Germany in order to get it supplied reliably with renewable energies. And this is a very complicated model, as you can see here. It has as input the different sources of energy, and it combines with the different needs, and output is, of course, what we need to have. And of course, a key element of this very complex model, which extends to the year 2050, is that we need storage, battery storage, pump storage, methane storage, heat storage on all these steps. So here to summarize once more: electricity, heat storage, and chemical storage, which includes hydrogen and methane. And if you run the model, you even get concrete numbers like 24 gigawatt hours of stationary batteries, 33 gigawatt of electrolyzers, 320 gigawatt hours of heat buffers, and so forth. And of course, these numbers are not yet final, because you can, of course, run this model in different ways. These were the results of a modeling looking for the lowest cost solution. But the message is very clear: storage will be an enormously important integral part of our future energy system, and therefore in itself an economy of that has to be watched. Most interesting for us and in our session is the topic of hydrogen. Hydrogen that can be, of course, generated by electrolysis. This is what we call green hydrogen, or it can be created from fossil sources, and then it is blue or gray hydrogen. Blue meaning it is from fossil sources where the carbon is sequestered by carbon capture, and gray hydrogen, of course, if CO2 is released in the atmosphere. And the hydrogen can be stored in many different ways. It can be stored at elevated pressures, and this is as well what we use in cars. It can be liquefied. It can be stored underground. And of course, we can use this hydrogen in many possible ways to regenerate power, to use it as fuel for mobility with the help of fuel cells, or, and this is an enormously important new area, we need it in the chemical industry to decarbonize chemical processes like steel and concrete processes. And of course, for underground storage, we should not be too afraid, because as a matter of fact, today we are already storing natural gas underground, and natural gas is as well potentially a dangerous material. So we are used to be able to store flammable gas underground in a secure and safe way. And of course, this really allows us to store enormous amounts of power. So I would like to summarize this short introduction to our session, that the world is heading into a period of rapid growth of harvesting solar energy by PV and wind. Wind is, of course, as well a result of solar energy. But PV has become the lowest cost way to produce electricity, driven by the gigawatt scale production and the technical innovations. And in order to generate a stable power system, we need to employ various methods of energy storage. And in addition to using it for energy storage and for transportation, we need as well enormous amounts of hydrogen, and this has to be green hydrogen for the decarbonization of industry. So I think the topic of our session today is a very, very timely and important topic, and I'm really looking forward to our lineup of speakers. And I would like to call for the first presentation by Elina Bosch from our Becquerel Institute on the competitiveness of PV storage and solutions.
So my presentation will be focusing on the competitiveness of PV+storage solution. Before I start, presentation of the Becquerel Institute. We're a research and strategy consulting company on PV technologies and markets. We're based in Belgium, but we have clients and are active in organization or research projects across the world, so Europe, Asia, Middle East, Africa, and America. About my presentation today, I will be giving a quick introduction first. Then I'll provide some insights on batteries, market, and prices. I'll be then presenting a few business cases of PV plus ESS, so energy storage systems, a few examples and competitiveness results before concluding. So the interest for storage has grown rapidly recently, as it was recognized as a necessary and relevant solution to reach a decarbonized electricity mix. And this also translates into the definition of national or regional ambitious targets related to storage with batteries or storage in general. And these storage capacity targets are part of more general decarbonization plans. So, for example, a recent study from the European Commission has a key finding that more than 100 gigawatts of battery storage capacity would be needed by 2030, or the US Energy Storage Association has adopted a target of 100 gigawatts of energy storage by 2030 as well. So this underlines that storage is necessary and it's recognized as a relevant solution. So the global cumulative battery market is still led by lead-acid batteries, but mostly for electric mobility applications, even though a plateauing trend can be observed. On the contrary, the lithium-ion battery market has been growing rapidly during the last 5 to 10 years, mostly driven by the electric mobility sectors, but also, as you can see on the right side, driven by the stationary storage market. And so the cumulative market is led by lead acid. Lithium-ion would represent about a fifth of the annual battery market, and then the remaining few percentage are shared between other solutions such as NAS or redox flow batteries, but which are still negligible. So this rapid battery market growth in the recent years has allowed both technological innovations and economies of scale, thus allowing important price decreases. So on the right, you can see the price decreases which were reached for lithium-ion batteries. And this is specifically for lithium-ion, since this technology benefited from the electric mobility market uptake. And even though quite important price decreases have been reached already, there are still further price decreases perspective, which are expected by the short to medium term. So moving on to business cases, there are different means by which you can value a PV plus ESS solution. Here in my presentation, I will be exploring 3 business cases. The first one being arbitrage, so storing electricity produced by a PV system during the hours of the day when wholesale electricity prices are low, and storing it to sell it later in the day or the next day when prices have increased. Another business case would be the supply of stabilized electricity in the sense of non-intermittent electricity to a city or a village where no grid infrastructure is present, so off-grid, small cities or villages or islands. And finally, PV plus ESS can also contribute to increase self-consumption rates of various electricity customers, residential to industrial. But in this presentation, I'll be investigating the case of a commercial customer. So for each of these business cases, the competitiveness is evaluated with relevant indicators and based on current techno-economic parameters for PV and ESS. And a second analysis is conducted with expected techno-economic parameters of ESS for 2030. And then, of course, standalone ESS can also be valued by providing grid management services through frequency regulation or a spinning or non-spinning reserve, depending on the selected technology, but this will not be the focus of this presentation. So in this first business case where a PV plus ESS is doing arbitrage, current NPVs reached with this combined system are negative. When we are taking into account the projected evolution of techno-economic parameters for ESS, the NPV crosses the competitiveness threshold in the United States. So both the south of the United States and south of Germany are studied here and displayed in the chart. But in both cases, the total NPV of the PV plus ESS system remains lower than the standalone NPV. So it could appear that currently the added value of an ESS is still limited. And there are 2 main reasons for that. The first one being that PV utility scale systems have already achieved such low LCOE that the LCOE is lower than the hourly wholesale electricity prices, and therefore that it is already attractive to inject produced electricity directly to the grid. And suddenly, even during hours during which the LCOE is higher than market prices, the extra costs of an ESS are not paid back by the revenues, and those revenues being based on the daily gaps between the highest and the lowest price on the wholesale market. So currently, the added value of ESS is limited, but it's important to say that the business case attractiveness should increase on the short to medium term. As presented, price reduction and technological improvement will contribute to make the business case more attractive, but more importantly, the renewable energy penetration, and more specifically the solar penetration increase, will lead to making arbitrage more crucial to efficient grid management, and thus paving the way to its monetization as such a service. Then constraints could also increase related to the injection of PV electricity to the grid under the form of curtailment, for example, which would reduce the NPV of standalone PV systems. And finally, daily price gaps between hours of solar energy production and hours of peak consumption could also increase and favoring this business case. Moving on to the second explored business case of supplying a small city, off-grid city, with stabilized electricity. So we have PV production, which is either directly supplied to the city, and part of that remaining production is stored and used later in the day or in the next day to fulfill the city's complete electricity needs. So there's still a large part of the PV production which remains unused. And because of this large part remains unused, the LCOSE, so the levelized cost of stabilized electricity, reaches higher levels than a diesel generator, for example. But it should be reminded that this business case should not be excluded, even though results could appear as quite negative, because the consumption pattern and the electrification rate of the considered off-grid small city have a huge influence on the results. And in addition, it should also be considered that the PV plus ESS solution is a non-polluting and silent solution compared to diesel. And in remote areas, such as islands, the fuel delivery by ship can also significantly increase the cost of generating electricity with a diesel generator. And there are also risks of spillages which are linked to this. And therefore, the business case remains still attractive. Finally, the last business case considers a commercial electricity customer which wants to increase its self-consumption rate by installing an ESS. So in both cases, the NPV of the PV plus ESS is positive when considering both the current ESS prices and ESS prices by 2030. Nevertheless, the NPV of the PV plus ESS system remains still at a slightly lower level than a PV standalone system. But as reminded previously, as the solar penetration will increase, the constraints related to PV injection to the grid will increase, either under the form of curtailment, but it could also be under the form of lower injection tariffs, and thus it will increase the need for higher self-consumption and consequently favoring the PV plus ESS business case. Once again, results are of course closely tied to the company's consumption pattern. In particular, with industrial customers, consumption patterns can really vary from one industrial activity to the other. And results are also linked to the country which is studied, with the electricity prices that are applicable in the country, but also if there are any PV capacity limits for self-consumption. So here in the studied case, it's Germany. There's a limit of 750 kilowatts, above which you're not allowed to self-consume. The whole production needs to be injected to the grid. And since there's a slight gap between the NPV of PV plus ESS and the NPV of a PV standalone system, it's not excluded that in some countries, when certain parameters or favorable conditions are met, that the PV plus ESS under this business case could already be competitive. So to conclude, it can be said that the technologies for ESS can already be considered mature technologies, both from a price or technological perspective. There were already significant price reduction which were achieved and technical innovation for lithium-ion batteries, but for other technologies as well. And even if the market of batteries has grown rapidly recently, the ESS market under the PV plus ESS configuration still remains limited. Then when investigating the business case based on arbitrage, it appeared that currently revenues from shifting the PV production to times of the day when electricity prices are higher does not result in being profitable yet. And when self-consumption based business case or the supply of stabilized electricity was explored, it appeared as already potentially attractive if some parameters and conditions are met. When looking on a larger time scale, so maybe medium to long-term competitiveness, the current market and regulatory conditions did not allow PV plus ESS projects to be attractive yet. But as the PV penetration will increase, and this will be observable across all regions of the world, there will be more favorable conditions for PV plus ESS competitiveness. In particular, as I mentioned, higher daily price gaps on wholesale electricity markets, but also more constraints related to the PV electricity injections under the form of curtailment or lower injection tariffs. And also there will be an increasing necessity and consequently monetization possibilities for grid management solution. And when having a broader perspective, if we want to achieve national and global targets in terms of contribution of renewable energy to the electricity mix, storage solution in whatever form are essential and crucial for an efficient grid management. And here my presentation focused on PV plus battery-based ESS, which are able to shift a part of the production at the scale of one day. But the interest of storage, of course, extends to a larger time scale by shifting the production at the scale of a month or a season with seasonal storage. And this is where other storage technology come in, such as hydrogen to purchase this one. And that's all for my presentation. If you have any questions, we'll be glad to answer.
Yes, thank you so very much, Elina. A very interesting presentation. I see a couple of responses on the question and answer channel, actually mainly comments rather than questions. Chris Lefebvre is impressed by the price difference, $100 per kilowatt hour battery versus 1 cent per kilowatt hour of solar production. However, of course, this is not any valid comparison, because the $100 per kilowatt hour of battery is the cost of the box, with the battery box, which can be, of course, charged and discharged many times. So if you have $100 per kilowatt hour battery and you have an average lifetime of 5 years or more, then you can come to below 10 cents per kilowatt hour for the cost of the stored electricity. Or do you want to say something about the cost of the stored electricity, Elina?
No, you're right. It's indeed, we have in mind the costs of PV electricity, and then when compared with storage, the gap can seem quite impressive. But as you mentioned, storage over its lifetime contributes to generating multiple times electricity, and thus the comparison cannot be made just on this indicator.
Yes, and our friend Winfried Hoffmann suggests that it is a good idea to show the price decrease for lithium-ion battery in a logarithmic price experience curve, because then you can see it looks exactly like we have it in photovoltaics, you know, price coming down as a function of globally installed quantity. Have you seen such curve also, Elina?
Yes, so when we consider battery scale, so not container on the ESS, but the battery system, the battery itself, on the last decade, learning rates of around 16% can be observed. Yeah. So it's quite significant decreases.
Yes, very good. My question to you is, Elina, one of the interesting business cases would be, of course, as well, private customers who offset the quite expensive household electricity rate. Did you as well calculate a business case for this? Because I think this is already very profitable with today's prices.
Yes, so I did not conduct the calculation for this case, but since for residential customers, electricity prices are even higher, the savings on the electricity bills, thanks to self-consumptions, are even more important. So I guess the yielded NPV would be even more favorable.
Yeah. So I think there we can really already today make a pretty favorable and cost competitive case for energy storage. Absolutely. Okay, I see there has been already a lot of discussion about blue and green hydrogen, but I would like to shift this discussion after we have had the presentation specialized on this topic. So Elina, I would like to thank you again. And then we are 2 minutes ahead of schedule. This is fantastic. We come to the second presentation of our session by Hugues de la Baume. He is the co-founder and CFO of AZA Battery, and his topic is batteries, a game changer. So Hugues, you can share your slides now.
First, Eicke, thank you very much to allow us to present how zinc air can contribute to the development of efficient storage solutions for both on and off grid. Now, the question is, are batteries a game changer? Elina mentioned that already. And well, let's see if they really are a game changer. First, well, if we consider the game as being how to decarbonize the power grid, then the intermittency of renewable sources of energy is emerging as the single biggest obstacle. Today, pumped hydro is near maximized, so the solution seems to be batteries. And they also have the advantage that you can easily transport them and put them where you want. Now, sorry, I've got a bug here, yeah. Now, Bill Gates, said already a few years ago that all the batteries on Earth can only store 10 minutes of the world's electricity needs. It has changed a little bit by now, probably, but not by that much. And today it is mostly lithium battery projects which are underway to replace peaker plants or to complement solar and wind. But despite lithium being around for many years, things are de facto moving very slowly. So, so scaling up, what we have now is maybe not the solution. A game changer seems necessary for grid storage itself. And why is that so? Well, because increasing the scale of what we are currently doing will probably not reduce the cost sufficiently, despite what I just heard previously about the this exponential decrease in cost of lithium batteries. When you work inside of the world of batteries, you realize that things are not that simple. Storage economics are different from PV or solar panels. Sure, increased scale may yield some advantages, and certainly lithium technology is improving. But nearly all experts agree that scaling lithium will not reduce cost sufficiently. In grid storage, we need massive cost reduction of other orders of magnitude. Scaling up will also not solve safety, environmental, or sourcing problems which are specific to lithium. So basically, storage must be cheap. It must be also green, it must be safe, it must be circular. And lithium storage is none of these. If you want something to be truly cheap, it must be made from plentiful materials. It must be manufactured in a low-tech environment. It must be reliable and easy to ship. It also must be green and safe and easy to recycle. The current solution cannot be cheap because lithium is none of these things. It is toxic and its extraction is an environmental disaster. Lithium catches fire when it is exposed to air, and lithium batteries use flammable electrolyte. And to mitigate this requires sophisticated fire suppression, cooling systems, and highly technical battery management systems. In addition, you can only extract battery-grade lithium from a handful of countries, many of which are presenting some problems. Lithium is as dangerous to ship as fireworks, and it is almost impossible to efficiently recycle it so far. So because of its chemistry, it can never be truly cheap, no matter how much we will scale it up. At least that's what we can understand from our analysis and what we've seen in recent years. So what's the solution? You understood already. The solution is zinc air, or a technology that would bring some benefits as zinc air. And we're developing that technology for over a decade now. Now, let me give you a word or two just about the technology briefly. The ASA battery use a pasted zinc electrode. It's important to distinguish that because you will have heard a lot about zinc air batteries. Most of the time, there are flow batteries, which are much bulkier with a power density much lower. They have their own advantage, but that's not what ASA is. ASA is much closer in terms of form factor, energy density, and other benefits to what you have with a lead battery or lithium battery, the same kind of volume and energy density. So it is actually, in terms of energy density, quite similar to lithium LFP. So the shape of these cells is prismatic, and they weigh about 2 kilos each, which means something very different from flow technology and other zinc air type of batteries that you may have heard of. So what I'm telling you here is that zinc air is cheaper. It's cheaper. We modeled this with the help of Becquerel Institute, for which I want to thank again Elina and her team. And the conclusion is that a solar farm by 2030 will have a levelized cost of stabilized electricity, which will be about 40% cheaper when using zinc air batteries versus using lithium batteries. The price will have dropped from about 9 cents per kilowatt hour today with lithium batteries in 2020, down below 3 cents per kilowatt hour using zinc air batteries in 2030. And many factors are at play to explain why zinc air is much cheaper. Let me give you a few of them. First, the production process is much simpler for zinc air. There is no need for clean room technology or thin film technology. It is much closer to the low-tech lead battery production process, for instance. And that's very important because most of the cost associated with with the lithium production, I'm talking only about the production process here, is really these high-tech processes that are being used. It's not the case for zinc air. Second point, it's much cheaper and easier to dispose or to recycle zinc air batteries. Zinc air batteries are being recycled zinc batteries are being recycled today already. And so the infrastructure is in place. Third point, the bill of material is less. $12 per kilowatt hour versus $40 for lithium. Fourth, cells are generally of a bigger format, about 2 kilo for zinc air cells, which gives it some economies of scales as well at the level of the system. Number 5, there is no need to add costly thermal control and fire mitigation systems. Number 6, less fire risk means less fire risk, also less environmental risk, and finally less financial investment because the capex are much lower for zinc air than for lithium. All this will mean cheaper damage insurance, cheaper insurance to replace equipment, and also cheaper insurance to ship the equipment. Point number 7, less complexity to install the battery system. When you install a lithium system today, it's quite complex. It has a lot of specificities because of the fire risk and also the sophisticated BMS, which is specific to lithium to control the battery system itself. So in a nutshell, zinc air is cheaper, but it also is safer. You probably remember a few unfortunate events that took place with lithium batteries. To the contrary of lithium, zinc air batteries do not need cooling or thermal control systems to operate safely. This is due specifically to the zinc air electrochemistry. And because the materials are less dangerous, the batteries are less dangerous for us to manufacture, less dangerous to transport, and less dangerous to recycle. Zinc air requires less complex BMS systems and doesn't lose performance under high temperature, which makes it safe and also well suited for hot climates. And as you know, there is a lot of demand for storage systems, ESS, in hot climate zones. So that's a very key parameter. So zinc air is both cheaper and safer, but it is also greener. So zinc is non-toxic. We even use some of zinc pills as a supplement for our food, as well as the other key components of the battery, which are mostly carbon and potassium hydroxide. So nothing really scary there. And the zinc mining process is well understood for many years and controlled and does not cause environmental hazard when it is performed properly, of course. Another key benefit of zinc air batteries is that they are recyclable. That's something that most of us are becoming more and more aware that it's a key feature of the future for batteries, recyclability. So the thing is that the zinc recycling infrastructure does exist today already because many products are using zinc as a component, including zinc carbon batteries, which are recycled today already. So many processes to recycling cost efficiently zinc are already in place. And that system is done at a fraction of the cost of recycling lithium batteries. Although it's not yet clear that recycled lithium is actually of sufficient quality to be used again in batteries. I think we need about 98.5% purity for lithium. And maybe so far we are only talking about disposing of lithium batteries more than actually recycling them. Volkswagen is only setting up its first recycling pilot plant. I think they began in 2019. And a lot of R&D is still expected to take place to properly recycle lithium batteries. I think now we are at 57% of components or something like that. and the cost efficiency of the lithium part itself is extremely complex and not cost efficient for sure yet. To give you an indication, order of magnitudes, and it's still very early in the game to be sure, we have an indication that currently a proper estimate of recycling cost is about $6 for zinc air versus 60 for lithium. I'm talking per kilowatt hour. So it's an order of magnitude of 10 for the recycling cost, but we're not even sure we can really recycle that lithium from the batteries. It's a supposition still, while the zinc is already recycled from batteries. Zinc air batteries are designed and suited to be part of the circular economy. And because the storage systems will be massive, it will be absolutely necessary that they are completely recycled, not 50%, 55%, 7%, no, 100%, or at least 95, 99, something decent. And this will be both for environmental and for economic reasons. Now, another aspect that favors zinc air is that it is widely available. You've heard a lot probably about the problem of sourcing lithium and the impact it can have at different levels. Well, sourcing for zinc can take place in very large quantities and from many locations. It's widely available in Australia, in China, in the US, in India, in Europe, in Canada. It's almost everywhere. And finally, well, to come back to our zinc air batteries, let me tell you a few points for the one who might be thinking about installing some systems already on their solar farms. Our system will be available in a standardized containerized solution and also in customized format for specific applications. We anticipate addressing in priority the needs of solar farms and of large commercial installations. And it is important to keep in mind that safety and low capex intensity will favor the bankability of zinc air, which will help greatly for the financing of large solar projects. And the objective is to be as close as possible to a plug-and-play solution that's safe, easy, inexpensive to transport and to install, to maintain, and also eventually to decommission. So voila, there is one last point that I would like to bring forward before I can answer your questions. It is about PV plus storage. It is actually that zinc air is offering much longer duration storage. And that's important because today, when you look at requirements for solar farms, usually we talk about 2 hours, sometimes up to 4 hours storage, which is the current standard, but no more, because it's way too expensive. And zinc air can do much better because it is much, much cheaper. So what we envisage is storage of 6 hours to 12 hours easily in a standard manner for solar farms, which will be able to provide the grid with stable power all day long. Also, full solar-based autonomy for off-grid becomes energy competitive with on-grid because the cost will be so low for fully stabilized electricity thanks to the combination of PV and zinc air together. So with zinc air, energy storage does not play any longer the role of a simple backup or optimization solution like is often still the case with lithium. And now storage will become a full partner together with PV. And PV plus storage becomes finally the alternative electricity provider. That's our goal, and that's why we want to bring zinc air storage to PV and to the grid. Voila. So thank you very much for your time and for your attention, and I'm happy to answer your questions now.
Thank you very much for this very interesting presentation, and I think we will have a few questions. My very first question to you is, can you explain a little bit your time scale development? When do you expect to roll out commercial products?
Thank you, Eicke. Well, we expect to do it, we expect to have the first stationary system demonstrator available within 2 years' time from our pilot production line starting production, which would mean in that case to have commercial solutions available within 3 to 4 years' time, let's say 2024.
Okay, so there are still serious technology problems you are still working on.
We still have, we always will have technology problems because we always want to improve the product, obviously. It's working pretty well already. We want to increase the number of cycles, obviously, because it's going to improve further our competitiveness versus lithium or any other technology. We consider that today we're already competitive with lithium ferrophosphate, the cheapest type of lithium. In 2022, we'll be already 20% cheaper than lithium. Here I'm talking about the stabilized cost of energy. I'm not talking about the capex, which is already 4 to 5 times cheaper than as investments in the battery system. And so yeah, it's mostly about increasing the number of cycles. We're working very hard on that. And we believe that with the extra financing that we're working on, we'll be able to accelerate things further.
Very good. Very, very promising. There's a question from Diana Powers. Can these batteries be used in electric vehicles?
We plan to use them as well in electric vehicles, especially for mass of fleet vehicles, automatic delivery type of vehicles, or heavy duty vehicles. It's a battery that has eventually as much energy density as lithium, not necessarily as much power density, more like a third or a fourth of that. So it will be fine to drive around, you know, with your UPS truck to deliver parcels for UPS or for Amazon at 80 miles an hour, but you're not going to use it for a Tesla, which wants to be a very high performance battery. But yes, definitely we plan to have those batteries eventually being used for electrical vehicles, but that's not our first focus. Our first focus is really to deliver solutions for stationary systems because we believe that's where we can move faster.
Yeah, this I think the same. There is a question from Sylvia Lamati. She asked, of course, after what you said just a moment ago, how many cycles can you reach right now? Can you disclose this to us?
Sure, of course. It depends, of course, on the type of cycles. I mean, we can do thousands of cycles and there are some specific circumstances. What we like to present always, because we're talking to battery experts, people who develop other technologies of batteries. So we always talk about number of cycles at 100% depth of discharge under the most difficult circumstances. And so we don't take into account all the benefits of, I would say, charging and discharging less than 100%. So in that case, we've got beyond 500 cycles already in zinc air. You have to know that 10 years ago, it was 0 cycles. 2 years ago, it was only about 150 to 200 cycles. So these things are moving exponentially fast. And we're very optimistic that we will have thousands of cycles in the future. But today, with those 500 cycles, we're already competitive with lithium. But of course, we would not keep our batteries in place for 5 or 10 years. We would change them after 3 years already. But taking into account the cost of removing those batteries, recycling them, putting new batteries, after 3 years, we're still competitive with lithium already, before moving forward in number of cycles.
Very good. And Winfried Hoffman asks, what is today's price per kilowatt hour? Probably you want to say something today, and of course, where you what you target. That means the cycle time for a kilowatt hour cycle through the battery.
So if I understand well, we're talking about the price of the battery packs, the hard.
No, we're talking about the price for electricity that has been cycled through the battery.
Okay, right now we consider we are around 4.5. Well, it depends on the location, but I would say 4.5 cents stabilized electricity, let's say in Spain.
Yeah. Axel Sulet asks, he says, it seems like a dream. Why is lithium still the technology Europe manufacturing is considering, for instance, in the Verkor project?
Well, because lithium started before we did, and they're ahead. They're ahead in terms of industrialization. And we still have to go through that phase. And as you know very well, it takes time. And lithium, if you remember a few decades ago, we had lithium batteries at home we were using for toys, for all kind of things. They were not rechargeable. We were buying them in the market, in the little shop around the corner. They were lithium batteries. They were not rechargeable. They became rechargeable eventually after many years. We didn't realize that. And when they became rechargeable, suddenly many applications used rechargeable batteries, lithium ones. Well, zinc air has been in existence for decades, Zinc-Air does exist. It's already marketed. There's about 400 million euros of batteries Zinc-Air sold every year, but there are primary batteries. You cannot recharge them. So our challenge and our goal is to make Zinc-Air completely rechargeable. And that's what we've started 10 years ago, and that's why we've moved along the curve, so well. And now we are at a level where we can actually compete with rechargeable lithium.
Yeah. No, I think very exciting. Brian, did you want to add something because you said you want to answer this live?
There's a question from Brian, sorry.
No, Brian,
I didn't have any questions, sorry.
No, but in the Q&A, you said you want to reply live, but maybe I misunderstood. Okay.
Oh, yeah, no, once the question's answered, I'm, we'll say, Xing it out so that you don't get confused between the other questions.
Great, great. And Chris Lefebvre, this is maybe a nice closing question, is won't electricity needs explode, and therefore will solar PV production and storage capacity explode also? I guess we both agree that it will explode, as a matter of fact. Maybe Hugues, you want to say something?
Well, sorry, yeah, definitely. I mean, storage capacity will, demand will keep exploding. You can see the numbers already, even with current lithium systems in the US in particular. It's mind-boggling. The demand is huge. And you see thousands, just for California, 4,000 solar farms in the pipeline for the next 7 years already applied for permit to connect to the grid. 4,000 solar farms just for one state in the US. And they usually have a size of 50 megawatt or more. So all these entities need storage. Most of them need storage. And you can see that when you look at the duck curve that you saw on the second slide, it's a major problem that just keeps increasing. So we need massive number of stationary systems, absolutely.
Yeah, and as we have still 2 minutes, Weini Chen asks about the round trip efficiency and discharging rates. So first of all, round trip efficiency, this is in the order of 60%, or what would you
That's
say?
correct. That's correct. It's 55 to 60% depending on the setup that you have, but let's say we'll be at 60%. It is specific to the electrochemistry, so to zinc. So there's not so much we can change. I mean, we can hope maybe one day to move to 65, but let's say 60% is a good number. And it is increasingly less of a problem, obviously, as the marginal cost of kilowatt produced by photovoltaic keeps dropping.
Yeah.
And as Elina said earlier, this is increasing. The speed at which the price of photovoltaic drops is faster and faster. We're moving towards a marginal price of 1 cent per kilowatt hour. In that case, when you have almost free electricity, the fact that you waste some in your system is marginally, is much less important. Of course, if you lost 90%, it would be quite sad and probably not that efficient. But between having 60% or 80%, it doesn't make a big difference in the end, really. What's important is the price of stabilized electricity outside of the system, PV plus storage, and PV plus Zinc-Air storage. Our aim is to have electricity stabilized at 3 cents per kilowatt hour in rich sunny areas in a few years. And in places like Belgium or like Germany, to have that around 4 or 5 cents maximum. Yeah.
And I guess similar to PV, you don't foresee any limits as to the speed with which we can scale up, because zinc is a very abundant element, so there should be no bottlenecks or shortages if we want to, towards the end of this decade, have really gigawatt hours of Zinc-Air storage available.
You're absolutely correct, Eicke. It's true, and that's a massive issue that we talk as an academic subject most of the time, but it is a very practical problem now. And when you look at the numbers which are presented for storage, you're talking about hundreds of thousands of tons of metal that you need to make this battery storage operate. And you can't do that easily with lithium, especially if it's already consumed by a lot of vehicles and other applications like your laptops and other mobile applications.
Yeah.
So it's very, very, very likely that an alternative technology such as zinc air, because of the wide availability of the metal and the very low cost of it, is going to displace lithium for stationary systems.
Yeah, in the second half of this decade, I guess.
Yeah.
Okay, excellent. Thank you very, very much. This was a very interesting talk for all of us, and it shows that the question of battery storage technology is by far not yet solved. We are really very excited about these options. We are now changing gears a little bit, and we go and concentrate more on the hydrogen topic. And this will start with the presentation by Lionel Perret from Planair, and he is the director for renewable energy at Planair, and his title is Competitiveness of PV Solutions. Actually, we see the title, PV and Hydrogen Solutions. It's yours, Lionel.
So I'm Lionel. I will present you then this presentation about different application of PV and hydrogen technology. First, a few words about Planair. So we are engineering and consulting company, and what we bring is really engineering. We try to test and to operate what we are speaking about, but we also do some vision and some consulting about new 100 renewable energy system, including hydrogen, and we develop our own patents and algorithm for modeling this new energy system. And I will present now some application case from the small scale to the larger scale, where we, for most of them, been involved in the planning of this system. If I go from the small scale, it's a German solution. You've maybe seen it in some different fairs. It's this HPS PCR where they try to standardize. It's a main issue in hydrogen is trying to standardize a product. And so HPS, they try to standardize a product for houses. It's not yet profitable because it's about 70,000 euros, the cost of everything. But you can be completely autonomous with this system using a battery, a fuel cell, an electrolyzer, and seasonal storage. So it will depend if it becomes competitive on the price evolution, but there is yet solution in being tested. Also, there is 2 sites in Switzerland where they buy this device and several sites in Germany. We see also we have a case in Switzerland in a collective building, also with full coverage of solar. Here we see it's quite interesting because they put all the cost of this complex system, including also hydrogen storage and full PV coverage, heat pump of 20 kilowatts. They put the cost in the renter fees. So as it is a new building, it's then the cost for the energy is quite higher, but at the end, the cost for the renters is not so much higher. So this building is full of inhabitants, is not connected to the electrical grid. So it's also interesting because it changes then the way looking at the total cost of the building renting and not only of the cost of energy. And it's as attracting enough people to be full. Another application where we've been involved is on a solar boat, where you have also here even the desalination system, the hydrogen production, the electrolyzer, the compression. So the main challenge is in the combustion in this boat, and then also the fuel cell to produce the electricity to try to be fully autonomous and to be able to go around the world with this boat. It works since 2 years, and we see the hydrogen is not much a large part of the energy provided, but still it's a very important part where there are lackings of energy, even if there is large lithium-ion batteries, but hydrogen keeps then the fuel, the boat running when there is not enough sun or wind. So we can apply it also the same dimensioning as the system for island. We've been making some case for different islands. One of them was the Easter Island, now Rapa Nui, where we consider different energy system. There is a potential also to have a kind of a base production also with the plastic waste and with pyrolysis. It makes a little of the part, but then the main potential is PV, and we consider different mix of storage. And what we see on this island, which is really a very remote island, the costs, if you include the subsidies, the cost of electricity in this island is today almost 70 cents per kilowatt hour. So here you are already with this system completely profitable. You just need to put this technology in a so remote place, but you can be competitive with this an investment of about $30 million. You have, compared to the situation today, to the cost of electricity today, a payback time around 7 to 9 years. And how this system will work, we've made the full calculation with every hour's balance. So in winter, which is in June in the Easter Island, you will really use your hydrogen as a backup when the PV and battery system is not enough. We have this small advantage of having also this use waste production, this pyrolysis, helping a little, but it's still a small part because the waste resource is limited as everywhere. And we see when there is some excess still of PV, you can then use also a little part to charge again hydrogen at the end of a critical period where the sun was very low. With this dimensioning, it was a cost optimized dimensioning. As mentioned also in other presentation, you have big excess of PV, but it's not the problem. PV is, even in this situation today, cheap enough that you can have bit excess in summer. You put what you can, what is reasonable in batteries and in your seasonal hydrogen tank, and then you have a flexible system for all the year, and we can show based on the historic curve that everything could work with this mix of PV, battery, and hydrogen on an island. There's also a tool where we can analyze different scenarios and play with scenarios based on this hourly simulation. We've also, with this study, make a publication in Frontiers Energy Research, where we published and discussed different scenarios we had. One was only trying to have the autonomy of the island with only PV and battery. We see here the system was not completely profitable. There were only 3/4 of losses. If we put then the hydrogen, we reduce by a good part the losses, and then if we have a mix, the system is also more profitable, and we reduce also the mix. So the mix of energy sources and the mix of storage is a key to be cost efficient on these remote energy systems. Another case study, this one is a kind of island, but in Switzerland. It's in a remote place in Switzerland where we had a customer. We have to supply a load during winter. So it is a continuous load to pump some water due to environmental restriction during the winter. And the only resource available in the area is solar, is sun. They could build a electric line, but it was something like 6-7 kilometers with a sensitive issue with environment. And it is very costly. So we try to design a system that will transform a PV production with its variability into the most constraining thing, a kind of continuous load during the winter where PV is producing the less. We consider a different scenario, trying how, if we could do it only with batteries, if you can do it providing a storage of hydrogen on site, or if we could do it having the electrolyzer and the fuel cell on site, and see what was the most competitive for this case. In this case, we are quite high, so we design also with bifacial solar modules. It's really interesting in this high altitude, and we have very good yield with solar in these areas in the mountains. We made the modeling, comparing the different costs of the system with different type of finding the right size of electrolyzer and of storage, having the simulation with PVSys, and then assessing the best cost solution, make the optimization, and then we get the different results. The one with hydrogen is quite interesting. It was also a question we had. Thanks to the batteries and the PV system, then we have a very small electrolyzer, but this electrolyzer is running almost more than 5,000 hours a year because of the PV and batteries, enabling it to run almost continuously. So it's today small electrolyzers are expensive, so we try. The optimization was really to try only with PV and battery to optimize its use to have a kind of continuous use. A small power, it's only the electrolyzer is only in this case 4% of the peak power of the PV plant, but it was the optimal dimensioning in the today condition. And then the fuel cells, which really provide this energy when it is not provided by the sun and battery in winter, is at a higher power and enables to produce a continuous power during the winter. If we compare the different scenario, we see that compared to only the case with PV and batteries, using hydrogen enables to have around 50% less of PV and around 70% less of batteries. And then it's a small system, it makes all the system competitive compared to the grid connection. So now this project is moving forward. It's in with the scenario 3, having the complete chain of hydrogen on site, because it's a remote site where also the transportation is at a high cost and the access is not possible in winter. So we will see we have a kind of island only running on PV in this case. If I go to a bigger scale, I can mention a special move also in Switzerland. It's a really smart move, finding where is the best market for hydrogen today. And we have in Switzerland now a contract for 1,000 Korean truck. It is really very profitable because these hydrogen trucks are exempted for the tax for transportation in the Alps, are exempted from the tax on oil, and can be subsidized with the high price of CO2 in Switzerland. So it means you have a kind of niche market for high price hydrogen, and then for green hydrogen if you want this exemption. So it's really give a push for hydrogen in Switzerland. We need now more than 7,000 tons of hydrogen, and we see now 2 large electrolyzers. One is already operating, the other one is under construction, and there is plan to extend to very large, 22 megawatts, next to hydro plants where they are paying the market price and submitted to the market price. When we see the potential price of this hydrogen for this truck, we can see that even a PV plant with today price of electrolyzer could be competitive to provide this energy. It means that taking the price, including the subsidy in Switzerland for the PV plant, the price for an electrolyzer of 60 kilowatts. Today, you have already in Switzerland a business model because you can sold at a quite a good price this hydrogen, and you take into consideration also the CO2 certificates that can go to the producer in Switzerland. Is very high, but having this subsidy, you can already have a business plan for just having a PV and transform it into hydrogen for trucks. And in the model, in what you have also a price for having a battery. The technology is open, but to optimize the use of your electrolyzer. In this case, you see you have 3 megawatt peak of PV and 600 kilowatt of electrolyzer in the optimization. If we go even on a national level, as mentioned, we consider also some scenario for Switzerland, and we consider also an increase of the consumption, taking into account the electric mobility and additional need for heating in winter, going to heat pump. So today, the electric consumption of Switzerland is about 60 terawatt hour, and here we consider a new need with the electrification, with a carbon neutral policy of 85 terawatt hour. And then we like other scenario considered, how we can realize this potential with PV and with storage. We consider storage with batteries and to see how the system will work. And we see already with this dimensioning where it's interesting to see that this amount of storage is more or less 2/3 of what could be in our scenario, the electric mobility capacity of the battery in the electric mobility. So it can even be done with a smart management in a large way by the electric cars. And in this scenario, you already have, when we analyze the hourly, you have no daily issue. You can already manage the variability at a daily scale, but you have an issue between summer and winter, where you have big surplus in summer and a strong deficit in winter. So what then we consider and we need is having a seasonal storage. Today, as a round trip efficiency, the hydrogen system are more or less 30 to 35 round trip efficiency. So as it was mentioned for the zinc air batteries, it's if you have cheap electricity, like in this scenario, most of this electricity will be curtailed. So you have in this scenario a lot of cheap electricity. Then the efficiency is not so much the issue. And what we obtain with the optimization, if we do that, it will still have some deficit in winter, having only PV in this scenario. But you can store in this scenario most of the surplus by the seasonal storage. And you see here how the battery behave, here is how the hydrogen storage behave. So it's hydrogen will be used in this scenario really as a seasonal storage. And we see really the time complementarity of the two technology. So if you analyze the two scenario compared to the situation today, having only PV and battery, we need a lot more of energy and we need a lot more of power. In terms having already hydrogen, the power deficit can be managed, but you still be lacking of energy. We see in this scenario, if we had some wind power, here we can have something better than the today's situation. So the tomorrow's scenario with hydrogen, wind power, PV, we have a solution also for the future supply of energy in Switzerland. If we see, it was also a question in the presentation of the cost. If we speak, it's engineer about the cost, what could be the total cost of this system? It's quite interesting to see because it strongly depends of what will be the price of this storage of hydrogen. If I put some hypothesis, it's quite open of what could be the cost for storing hydrogen in such big quantities of hydrogen. If I put quite high cost, I'm completely too expensive. Without a cheap seasonal storage, I'm not competitive. But technically it works, but it's not competitive. And if I find a way to reduce, I will mention part of the solution to have that, but to be able to store hydrogen at a low cost, I'm quite competitive with the cost of energy. I use the cost of wind and PV of today, not in the next 10 years. So with the reducing of cost of PV, wind, electrolysis, fuel cell, you can have, if you have also a moderate input of wind, you have a balanced system and you can be competitive. But the key is to find ways to have a cheap seasonal storage. And then there is different question, how can we have this cheap seasonal storage, this cheap huge storage? What we consider now, we have a study also for the Swiss Federal Office of Energy, considering using an old refinery and all these big tanks for filling them with liquid organic hydrogen carriers, this LOHC. There is different types of LOHC, but it's liquid where you can fill it with hydrogen without CO2, without carbon, but then you need heat. So if you have excess of heat, it can be really cheap, but it's being studied. What is interesting, even in this small Swiss refinery, what's the storage capacity of we have in these sites it represents 1 terawatt-hour of storage. So it's huge, and all the facilities there, it was planned to dismantle it. So it's now really the question, what could we do also with these tanks that are still working, but have no more use for the oil industry, but they could be a huge new storage for tomorrow. Another potential career where there is a lot of study in Switzerland is trying to make methanation using also some CO2 capture. Then it's you need all this CO2 chain, but it will enable you to use also and to create green methane. We see in Switzerland and globally a push from the people selling gas, pushing this technology and saying that gas network can be the green networks of tomorrow. At the end, it's an open question with a competition between different technology. What then I can conclude is that for this system and all the system we study, we see that we need, the first phase is having big surplus of renewable energy. We need to make hydrogen competitive, you need a massive solar deployment, and solar with the flexibility of storage, batteries, and hydrogen can really bring a large part of the solution. It is then more profitable and more efficient if you have also other sources, other renewable sources, and especially wind, where there is a really good time complementarity. But really the priority is try to get a big surplus of renewable energy. So if you want to push hydrogen, you have to push renewable energy. That's why we are also here today. This mix of renewable energy bring flexibility and bring competitiveness to the system. And then this storage, they need to be a cheap storage, they need almost free or green electricity. And then to have this cheap storage, you have to consider different molecules. It's more efficient. It will be ammonia, methanol, liquid organic carrier, as I showed, where you don't need this carbon, which could be interesting, but you need it. Liquid H2, gaseous H2, gaseous methane. There is a lot of technical option open, even more, but then it will be the key for having a 100% renewable system and a full transition to have cheap seasonal storage. To enable this, there is also a question about how to design all the energy system. We see and we think also that the grid tariff have to reflect this value, and you should get in the grid also some opportunity to pay the electricity at a really low price, also including low grid price. To this extent also, the energy winter has not the same values as energy in summer. It's maybe for PV not a good guess, but still for this hydrogen and for the storage of tomorrow, you need almost free electricity in summer. So having some policy giving premium in winter and having, for example, not the PV panels being snowed up in winter can be interesting. You need also, with this scenario, we see we are creating the climate transition. And so we need also in Switzerland to really link CO2 climate policies and electricity policies. And then we have a really interesting solution with, it was the example, or even with electric car, you have huge saving of CO2, and this saving should also remunerate the storage and the production system. That was it. Thank you.
Thank you very much. I think this was a very exciting presentation, and I think really the idea that in the future we will have electricity at almost zero cost has to still penetrate the thinking of many politicians, people in economy, people in the media, because really this changes the outlook on what makes sense and what doesn't make sense completely. You know, I don't understand whether carbon capture and storage should make any sense if we have excess electricity to produce green hydrogen and green methane completely artificially. My question to you is, Planair is only doing planning and suggestions. You are not in the area of implementing those models.
We are not having the technology, but we are implementing them as engineers, making the call for offer and following that it is well implemented. So It's yet new technology, but we try also to implement them. Part of the projects that I have mentioned, they are now in the, we are calling for offer and trying to find the best partner to realize them. It's quite a challenge with hydrogen because most of the technology are made for base load. And then when you want to use it with really flexible loads, there's still a challenge. And the biggest move in hydrogen is to have to create a big electrolyzer and having reducing costs. But we see really a value also in decentralized system and in middle scale system where the technology is not, you have a lot of engineering to do so that it works properly.
Yeah, yeah. But so that means Planair is thinking about even going into the construction part, or do you only accompany construction by your advice and your certificates and so on?
We are doing the planning, and we are following that it will works well, bring the thing together, but we are not creating the technology itself.
And you
what we are
don't give out
developing,
fundraising for the projects. You keep the interesting part of the story.
yeah, we have to do, we will do, not yet, I think, be responsible for the commissioning of it as a neutral engineer, as a planning engineers, but not bringing all the technology.
Yeah, I want to share one question which I got from Emmanuel Goy. After what you say, key should be then to reduce electricity consumption in winter in order to make this problem as easy as possible.
Yes, indeed, I mentioned also what you can save is have to be done, but still, if we want to shift all the need we have for heat in winter, we will still see an increase of electric consumption in winter. And also this cycle of renovating houses is slow. So still, if you want to if you want to be on time with what we have for the climate change, you have to still produce more electricity in winter. And that's
But of course, insulation then makes a lot of sense if you use electricity for heating and you store it by hydrogen. Very clear.
It's a part of the policy you must have.
Yes. But really, I think altogether your message is extremely encouraging, and it should as well be encouraging not only for Switzerland, but for all countries. Really,
I think in Europe it's more or less the same situation. In Switzerland it's a little easier because we have already hydro, which is quite flexible, but still when we put this additional need, this hydro represents only 40%, 30-40% of the need we have tomorrow. So then the big part of it is coming from solar. It will be good if we have a little of PV, but it's a challenge in Switzerland because wind potential is not so big. So we will really rely on PV.
Yes, and of course one should work on flexibilization of hydro. It would be a sin to use hydropower during the daytime when you can do it by PV. You should store the water during daytime and use it in the night when you really need it, right?
Yeah.
And in the winter, hydro does not completely freeze in the winter, I guess.
No, it's today. It's already our storage or seasonal storage, mainly these big hydro plants. So we have the project where we put a PV plant directly on one of
its. Yes, with pleasure. Yes. This is of course an extremely cost-effective combination because you have the power lines anyway from the dam, and then you connect the PV to the same power line.
It's also really a land use optimization to try to say, okay, it's really an issue in Switzerland, a land used for energy production. So let's produce more energy with it.
Absolutely. So Lionel, I would like to thank you again in the name of all the listeners to your interesting talk. And now we can go back if you revert the screen sharing, and we come to our last presentation. Last but not least, I would like to introduce to you Mark Rechter. He is the founder and CEO of Resilient Group and as well of MCPV to bring in the PV production into Europe. But our topic today with Mark is, of course, hydrogen. I see Mark is already there.
Thanks very much for the invitation to speak today. It seems that that hydrogen is accelerating globally, fortunately, and especially in Europe. So I'm very happy to share some of my thoughts with the audience today in terms of the title that you've asked me to talk about, which is hydrogen competitiveness in the European energy transition, which is a key element not only for Europe's energy future, but I believe also for Europe's economic future. So in terms of the agenda, I'll talk a little bit about Resilient Group and MCPV, because I think most of the people watching probably have not heard of us yet. Then I'll set a little bit of a context for the green hydrogen sector in itself, and the importance of European supply chains and the importance of integrated value chains within both the green hydrogen, emerging green hydrogen sector, as well as the PV sector, or the link to the PV sector. And then I'll close off with identifying some of the key goals that we have identified for green hydrogen, and also for the opportunity of bringing back PV manufacturing into Europe on the back of this, or partially on the back of this. So first of all, a little bit about ourselves. So Resilient Group is the holding company of a number of entities that have developed different types of projects and activities over the past approximately 10 years. Those activities are focused on three main areas. So one is solar PV. The second one is digitalization, and the third one is green hydrogen. In terms of these three, although they might seem dispersed, they're increasingly integrated, of course, because as the green hydrogen sector emerges over the next years, solar will most likely be one of the key technologies to provide very low-cost electricity to the electrolyzers, and so that's a perfect match, so to speak. And digitalization is increasingly, let's say, the layer on top of the infrastructures that will help us optimize, become more efficient, create markets, and create, let's say, systems that allow decentralized systems to function optimally and efficiently. So all of these three, therefore, are quite interrelated, and we're looking forward to a very exciting next 5 to 10 years. In terms of MCPV, I'll talk about it a little bit in the next slides, but MCPV is an initiative that we've launched in the latter part of 2019, looking to bring back PV manufacturing to Europe based on heterojunction technology, basically based on, let's say, the next generation of PV manufacturing technology. And I'd like to just briefly mention the core team that we've been able to accumulate to drive this initiative forward and actually turn it into a project over the next years. Perhaps a little bit back to hydrogen, though. If we look at hydrogen, and specifically green hydrogen produced by electrolysis, so not gray hydrogen produced by natural gas reforming, up until approximately 2019, there was not much belief, I would call it, you know, at the policy level as well as at the industry level, that green hydrogen would ever become a serious reality. And most of this was related to the economics of green hydrogen. Now we started to invest in green hydrogen around about 2017. And we started doing that basically because from our solar perspective, we saw that the continuing fast cost compression and increasing efficiency of solar PV systems would drive the levelized cost of energy of solar down to the already mentioned 1 cent, magical 1 cent per kilowatt hour level. within relatively short period of time. And I think that target is probably going to be reached within the next 3 to 4 years or so, at least in the southern regions of Europe. So that, let's say that realization, jointly with the pressure on governments to actively decarbonize the non-electric component of our energy system, and that still represents about 70 to 75% of our total energy system, which is not electric today, have driven the hydrogen opportunity significantly forward. And what you see here is a couple of articles from last year, where there was still some, let's say, careful optimism or perhaps some skepticism as to whether hydrogen could actually become an economic opportunity. Now, of course, 1 year later, and over the past year, things have changed enormously. There has been a enormous increase in the policy level, let's say, starting with the European Commission, but also at individual member state level, including Germany, the Netherlands, Portugal, Spain, etc. So countries and the Commission that have set very, very ambitious targets for Europe's, let's say, hydrogen economy or hydrogen strategy. And this has happened within a very short space of time, driven by this same realization that, in fact, hydrogen is going to play a key role in helping the European Union, but also helping the world achieve its 2030 targets and decarbonizing difficult to abate industries, as well as mobility, heavy transportation, shipping, airlines, etc. So a very versatile, let's say, element within the energy transition. But at the same time, let's say, a technology and a component of the energy sector that is still very much at the start of its scale up. Not from a technology point of view, because technologies are already broadly very mature, but from a scale up perspective, we are very much at the start of things. That said, there has now been some very ambitious programs launched by the Commission again, and also by individual member states. Germany, for instance, committing 9 billion to their hydrogen strategy over the next 10 years. And that is definitely going to see an enormous shift in the activity in the green hydrogen space. So what does that mean? Well, that means in some more detailed numbers that the Commission has identified a short-term objective for the installation of at least 6 gigawatts of electrolysis by 2024. That's an enormously short period of time, given the fact that the current global electrolysis manufacturing capacity is just about north of 1 gigawatt per year. So you can imagine that the whole industry requires a scale up in order to start meeting those kind of targets. And beyond that, from 2025 to 2030, the total capacity target is 40 gigawatts, and that's just within the EU. And so that's a massive scale up of electrolysis capacity, and also a massive scale up required in terms of electrolyzer manufacturing capacity. So very interesting and ambitious program that the Commission launched in July under the European Hydrogen Strategy. Very ambitious targets, and we're seeing a broad, let's say, backing by a number of member states who have identified this clean or green hydrogen sector as a major economic opportunity. Now, in terms of the link to solar, what does this mean? Because ideally, of course, we produce green hydrogen with clean energy, or let's say green energy coming out of wind, solar, hydro, ideally. And so ideally not electricity produced by coal plants, because then, of course, we miss the point. So if we look at this extra capacity that's been identified by the European Commission, we see that of the 40 gigawatts expected to be, or let's say targeted to be installed by 2030, even if only, let's say 50% of that capacity will run on solar, with a little bit of the oversizing need that brings along. Just that level of electrolysis capacity will require an additional 30 gigawatts of additional PV capacity in Europe. Now, that's not the only thing that's happening, though. There is an additional 40 gigawatts planned for deployment across Ukraine and Northern Africa by 2030, which will require an additional 45 gigawatts approximately solar PV capacity. So just this, let's say, green hydrogen scale up to 2030, which is the so-called 2 times 40 gigawatt plan, will induce an additional 74 gigawatt of solar PV capacity to be deployed in Europe, Ukraine, and Northern Africa. And of course, those become relatively interesting numbers when we talk about capacity, when we talk about investment, when we talk about infrastructures and supply chains and markets that need to be created for that. So this is a huge undertaking that the Commission has set. And it is a huge opportunity as well for Europe and European industry to capture this momentum and build industries around the green hydrogen value chains, but definitely also very much to build industries around the very much related solar PV value chain, starting, of course, with the manufacturing part of the value chain. Very well. So one of the projects and initiatives that we launched in early 2019 relates to the creation of a European supply chain, or a European supply chain strategy, perhaps better said. And the project is it's called Green Flamingo, and it was designed to connect the very low-cost, mainly solar electricity generating capacity in Iberia to the industrial heartland of Europe, which is located, of course, in the Netherlands and Germany. Actually, the area, let's say, beyond the port of Rotterdam into the area of the Ruhr in Germany, is the largest, or represents the largest chemical cluster in the world. And as you can imagine, that brings along enormous decarbonization challenges for that very large industrial base to meet the 2030 and 2050 targets. And again, hydrogen plays an enormously important role in that. The idea here was indeed to capture the very low cost solar in Iberia. And as a matter of fact, just last week, the Portuguese government launched a solar auction in which the world record solar PPA was again beaten in Portugal. Currently down to about 11 euro cents or 13 euro cents per kilowatt hour on a 15-year PPA, which demonstrates actually something interesting. It demonstrates that Europe has a massive potential for low-cost green electricity within its own borders. And of course, that's quite relevant when we talk about energy security, as well as building industries within our own borders. At the same time, we are seeing a big effort from, I think it is 12 or 13 gas TSOs across Europe to build a large pan-European hydrogen dedicated hydrogen pipeline system. And the little box on the right-hand side bottom of this slide demonstrates the interconnection, let's say, of the future hydrogen pipeline infrastructure that is being planned for Europe. However, that will take some time, as we know, also from the natural gas pipeline system. It will probably take 10 to 20 years before such a complete hydrogen dedicated pipeline infrastructure across Europe is in place. And we cannot wait, of course, for 20 years before we start using green hydrogen and before we create markets that allow this green hydrogen to be bought and sold in a very easy and efficient way. So that's why part of our supply chain has looked at the use of different hydrogen carriers from the so-called liquid organic hydrogen carrier, LOHC, oils that were mentioned in the last presentation, to liquid hydrogen, to so-called green ammonia, which in itself is a large existing market. So we are currently moving forward with this project from a let's say connecting perspective, connecting again the Iberian Peninsula to the industrial heartland of Northern Europe, and looking to accelerate the creation of the supply chain as well as the kickstart of the European green hydrogen market with that. The numbers on the right are, I think, quite relevant. The 10 euros per megawatt hour is kind of a magic number. It's the 1 cent per kilowatt hour that has been mentioned several times by several people today during this session, and is kind of the holy grail of solar. Now, as mentioned, we are already very close to that, given the last auction that was held in Portugal, and I believe that within the next 3 to 4 years, definitely on an LCOE level, but perhaps even on a PPA level, this kind of price level will be available across the Iberian Peninsula, which is definitely a game changer for many different solutions. This also another. Speaking through it, not sure who it is. Okay, that's better. Okay, so the irrelevant factor of that 10 euros per megawatt hour, though, when it comes to hydrogen, is that with the cost compression that the scale up of the electrolyzer industry will see also over the next 5 to 7 years, we should come to a price of, or rather, probably better said, a levelized cost of hydrogen of around €1 per kilo, I believe, towards 2030. Now, that's very relevant because the current cost of gray hydrogen, so hydrogen produced with natural gas through steam methane reforming, is between 1 to 1.5 euros per kilo, but that doesn't really capture the increasing price of CO2, of course, that we will likely see over the next 10 years. So my expectation is that by the time we reach 2030, that green hydrogen will be the most competitive form and type of hydrogen, unsubsidized type of hydrogen available on the market, and that will, of course, open up a huge market for this green hydrogen itself. Oops. Okay. Now, perhaps a little bit about the economic opportunity of this. So, setting up the supply chain is of course one of the key, let's say, targets of market creation for the green hydrogen sector. But we should do it in an intelligent way, I would say. So it is not good enough just to produce the green hydrogen at a very low cost, we should definitely strengthen our market by looking at what manufacturing basis we can create as this market scales up by again taking advantage of the quickly increasing demand and huge demand for electrolysis equipment that will evolve, but also definitely for the enormously increasing demand for photovoltaic systems and modules in this particular case. And so that is, those are two areas that from a Resilient Group and MCPV perspective, we have focused on over the past year or so, and now looking to implement both of those strategies. If we get that right within Europe, then we can actually create quite a bit of, let's say, leadership from a global perspective over the next 10 years, whether it is in electrolysis and electrolysis technology, whether it is rebuilding our photovoltaic manufacturing industry, but definitely all of the, let's say, related activities that come upstream and downstream from those. So including hydrogen refueling station networks, mobility, fuel cell cars, the digitalization part of it. So much needs to be done. And Europe is in an excellent position to capture that, that value over the next 5 to 10 years if we work in tandem with each other. So from an MCPV perspective, as I mentioned earlier on, we are currently moving forward to implement within the next 6 years an estimated or targeted 15 gigawatts of cell and module production. We are looking to do this on the basis of heterojunction photovoltaic technology, which is the next generation of photovoltaic manufacturing technology that will allow further improvements in efficiency, as well as a continued reduction in LCOE. And it will allow, let's say, a competitive industry around PV manufacturing to come back to Europe. So I won't go into too much detail on this right now, but this is a very exciting opportunity for Europe, and we're very much looking forward to work with a number of partners on the implementation of this. And then perhaps to conclude, 2 slides in terms of some of the goals around the green hydrogen and PV manufacturing sectors. If we look at green hydrogen, like I mentioned earlier on, we're looking by 2030 to produce within the EU a highly competitive, non-subsidized green hydrogen in large volumes. So that means that green hydrogen will become the, let's say, hydrogen of choice, both from a decarbonization perspective as well as from a pure economics perspective. If we connect this properly across the value chains, then we can create very significant sustainable economic green growth. So very much aligned with the Green Deal that the Commission has launched. We can push competitive industrialization in Europe based on some of the technology leadership positions that we already have that can be expanded. And we can also be first movers in terms of marketplace creation. So all of those very important, let's say, potential opportunities for European industry to capture. Beyond that, of course, there are very important intercontinental partnership opportunities if we look at this emerging sector as the entire global energy ecosystem changes and effectually accelerates its change. And of course, not to forget that one of the key reasons we're doing all of this is to make sure that we keep within the 1.5 centigrade warming limit that has been so well defined by others already. So we've listed a number of requirements for this, but mainly what is important in order to achieve this, these targets in Europe are the combination of cooperation between public and private sectors around creating offtake certainty. So we need to create a policy framework that provides stability and visibility for industry to make the large-scale investments that are required for this, and the offtake certainty that is required for this. It is very important also for the European member states and the Commission to create a level playing field, both from an external perspective, and of course the carbon border tax is one of the instruments under discussion for that, to make sure that there's no carbon leakage as we move ahead and ideally move faster than some of the other regions in the world. And there's an important role for SMEs as well, given that, of course, there are some inherent conflicts in existing large incumbent companies that may not allow the acceleration that is required to reach our 2030 targets. So most of the other points that are listed here, I think, speak relatively for themselves. We will need to work efficiently with the grant frameworks to make sure that infrastructures are deployed in places where they make sense. I think this needs to be looked upon as a pan-European or from a pan-European perspective, not necessarily from a national or pure individual member state perspective. And it is very important for, let's say, frameworks to be in place to allow European entities to continue their innovation in this sector. But most importantly, perhaps, we need to start implementation of projects, and we need to start now because the rest of the world, of course, is also very active in this sector. And if we want to capture this moment, we really have to start doing things. As a last slide, and perhaps concluding, looking at some of the opportunities and needs or goals of PV manufacturing, like was reflected in Professor Weber's earlier presentation, we are currently only at the onset of the explosive growth of deployment of solar PV. This will require an enormous amount of production manufacturing, which will require and which will produce jobs, which will produce investment opportunities, return opportunities. And I believe that this is one of the key factors of the energy transition that can bring long-term economic prosperity and perhaps some wealth distribution across different continents in the world. So I believe that Europe, as well as other continents, should definitely invest in and build their own production capacities for all the right reasons. Now, what we are targeting is very much focused on de-risking the value chain of solar PV in this particular case. We're looking at making sure that we have strong alignment with the downstream companies, meaning providing them with some de-risking in terms of their supply chain, but at the same time requiring some offtake certainty for longer periods of time. We're looking at some financial support that is really focused on accelerating the growth that is really required to build this industry. And so that financial support will be somewhat focused on gap funding, but also very much on the type of credit guarantees that allowed China to grow their industry very quickly about 10 years ago. And of course, we need to have a level playing field in terms of policy, meaning that policy should provide instruments that provide some benefit for local content, prefer low carbon content within the products, etc. So overall, I think that our goals within these projects are, let's say, ambitious and currently still high level targets. but we are quickly moving towards a very concrete number of projects that that we're looking to implement. And I think I'll leave it at that because of being at risk of overshooting my time, Eicke. So thank you very much for your attention, and happy to answer any questions if you have any.
Thank you, Mark. This was really a very comprehensive overview of where Europe is going in the hydrogen sector. I can tell you at the moment, I don't see anything in the question and answer section, that we are already a little bit over time, actually seriously over time altogether, but that was not your fault because we had shifted from 5:30 to 6 o'clock as a end time. I think what I would like to do is wrap up our session today. I think this session was an extremely important session because it really gave us a very concrete outlook where we are heading. And when I say we, I do not mean just Europe, I mean really globally. We are heading very quickly globally to the transformation of the energy system to be based on renewable energies, and this requires enormous buildup of renewable energies. And because these renewable energies, wind and solar, are fluctuating in nature, we have the accompanying needs for storage solutions. And I think today's session has shown that we have no shortage of technologies. We do have present technologies. We have incoming technologies like the zinc air battery systems, or like the hydrogen storage, which allows us unlimited amounts of storage capabilities. And of course, we have the slowly growing awareness among politicians. Yes, there is something moving, and this is an important market. It is important for the economies of the countries which were so severely damaged now by the corona crisis. And I think there is no better way than to use some of the enormous amount of stimulus money which has been assembled. And it's very good that this has been assembled in order to not only help old industry come back to where we were in 2019, but as well to develop now the new industries of renewable energy, of green technology, the whole green economy, so sustainable economy. These are the opportunities ahead. So I would like to thank again all our speakers, all our participants, and especially those who participated as well in the discussion. I think it was a very interesting session, and I'm happy that it has been recorded so we can share the link and distribute it after the session further. And with this, I would like to close from my side.